Hello everybody, I welcome you all on this tutorial on NumPy. In this tutorial we are going to build basic understanding of NumPy for building data science applications. NumPy is the fundamental package for performing scientific computation and data science in Python, as it complements and extends the basic functionalities of Python. NumPy provides basic functionalities for creating, manipulating and storing n-dimensional data via its extremely powerful ND array object. The important characteristics of NumPy are that it is fast and memory efficient and has built-in support for performing basic linear algebra operations. Not only this, we can complement NumPy functionalities with other scientific packages to have complete data science stack. Precisely speaking, if we look at the NumPy ecosystem, NumPy is the foundational stone and all the scientific packages and data science packages are built around the NumPy. For instance, CPy, which stands for Scientific Python, and Pandas, which stands for Python for Data Analysis, and Matplotlib, which is a basic Python plotting library, are all built on top of NumPy. However, before going any further, we would like to know how to install NumPy. NumPy can be installed via two different ways, and here we are going to follow the easiest path. We will simply go to the Continuum web page and install the Python Anaconda distribution. We will select the correct distribution according to our operating system and will follow the listed instruction for installing Anaconda distribution. That's simple, right? So once Anaconda has been installed, we will use it for building Python-based data science applications. For this tutorial, we will be using Jupyter Notebook as the front end for IPython. The Jupyter Notebook can be launched by clicking on the Jupyter Notebook icon installed by Anaconda in the Start menu, or by typing in terminal like Jupyter Notebook. Once the Jupyter Notebook starts running, we will see a web page opening in the browser with current directory listing, as can be seen over here. We are going to create a new notebook by clicking on the notebook and selecting Python 2. Now once we have a new notebook opened, we can start coding. Jupyter Notebook is made of different types of cells. Precisely speaking, there are three different types of cells. Here we will be focusing on the code cells, as can be seen over here. In code cells, we are going to write code and execute it. As soon as we execute a code, its output will be shown below it. For instance, let's import NumPy. So this is a code cell. Now let's go and run it. So for running, I will simply go to the cell menu and click on the run cells. Since this cell has no output, so we are just going to create another cell by double clicking below, and now write another part of code. Hello world. So let's go and run it. So, that's it. So we can also run a cell by using the shortcut Control Enter or Shift Enter. Let's get back to where we were. Okay. Now working in the notebook, we will often need help about Python and NumPy's APIs documentation. It is extremely easy to get help in Jupyter Notebook or in IPython interface. We can get help by simply putting a question mark and the end or start of our query. For example, let's get help about np.array. So we are just going to put question mark and run this cell. Running the cell will simply pop open the doc string. So let's close it. We can get the IntelliSense about the class name, function name or variable name by simply typing tab. So np.array. So np.array is basically the alias of NumPy ND data structures. So similarly, we can get extra level of help by using Shift plus Tab. Shift plus Tab will open the first level of docstring for any function signature or class constructor signature. Pressing Tab while keeping Shift key pressed will open the complete docstring in a separate window, as we saw earlier. So let's close it. Okay. Now once we have configured the system, let's get back to, in fact, Let's get back to understanding NumPy and its core functionalities. We will be starting by understanding the NumPy vocabulary. In NumPy vocabulary, we label a dimension as axis, and rank is used to tell number of axes or number of dimensions. For instance, a single dimensional array or list of elements has rank 1. A two-dimensional array or a matrix will have a rank 2. A three-dimensional array will have rank 3, and so on. Shape of an array tells us how many elements are there along each dimension. NP.array uses a tuple to encode the number of elements along each axis. For instance, this rank 1 array has shape of 1 with 9 elements, and matrix has shape of 3, 4, since it has 3 elements along axis 0 and 4 elements along axis 1. Size tells us total number of elements in the array, which is simply product of all the shape tuple elements. It is important to mention that as we add a new axis, it is prepended to existing axis. For instance, going from 1D array to 2D array will add a new axis 0 as rows, and existing axis will be moved to columns. Similarly, going to rank 3 will prepend a new axis. Thus, axis 0 will represent the page or matrix number, and axis 1 will represent number of rows in the matrix, and axis 2 will represent number of columns. The basic ND array class has built-in data members that can provide information about each array's axis, rank, shape, size, etc. We can simply access them by putting dot operator at the end of np.array instance. So for example, here I have created a two-dimensional array which has a shape of 2, 2. Its total number of dimensions are 2. Its size is 4. 2 cross 2 is equal to 4, and it's z.d type. D type is basically used to tell data type of elements. It can be any type, np.int32, float 32, or float 16. It is important to mention here that np data types are different than the inherent Python data types. Now let's dig a little deeper and see how we can create NumPy arrays. Technically speaking, we can create array via 3 different ways. The easiest one is by passing the existing Python list and tuple to the constructor of np.array class. This constructor will return us the created ND array, where the axis will be same as the number of dimensions of input data structure. So let's go and create arrays from this tuple. So let's is equal to executing it will display the shape of both the newly created NP arrays. While creating an array, we can pass different customization options to the constructor as the arguments. For instance, we can specify the data type of array for all the possible options. We can refer to the documentation of np.array class. So let's go and create an array from this two-dimensional list of type float 30, float 16. So C is equal to np.array of array d type is equal to float np.float 16. So now this will simply running it. There's no output. So here it is. So as can be seen, it's a NumPy array of float 16 data type. Second and most commonly used method for creating array is using built-in array creation functions. First set of methods are used to create 1D arrays with values from an arithmetic sequence. Arange and Linspace are two popular methods to use for generating sequences. So arange method expects 3 arguments: starting point of the 1D sequence, end point of the sequence. It is important to mention that endpoint is excluded, and the step size or delta between each elements. So let's create a sequence. A is equal to np dot a range of -5 to 5 with a step size of 0.5, and then let's go and print a, and then let's go and create b is equal to np dot a range of 1 to 10. So excluding the endpoint will have an effect of having step size equal to 1, print b. So here it is. So np.a range -5 to 5 with a step size of 0.5 will create a sequence by excluding the endpoint 5 with a step size of 0.5, and similarly by using np range with arguments 1, 10 will create a sequence from 1 to 9 with a step size of 1. Linspace is different in the sense that its third argument is not the step size, but number of elements to get between starting and end point, and thus help us overcome the floating point precision issues. So, for example, np dot, let's put c is equal to np dot Linspace of 0, 1 to 10, and let's ask him to 30. So this will have effect of having 30 equally spaced point to be sampled from 1 to 10. So print C. So here it is. It's also important to mention that the endpoint will be included in Linspace, but not included in A range. Second set of methods are used to create arrays with fixed values. Popular methods include np.0, np.1, np.fill. All these methods expect a tuple as argument. Number of elements in this tuple tells number of x's. For example, creating a 2D matrix will require us to pass a tuple with 2 elements. Here in this case, we are passing it 2, 3, so it will create a matrix with 2 rows and 3 columns. It is important to mention that not passing a tuple for a multidimensional array is a syntax error. For example, using np.0 with 2 arguments, 3, 2 for creating 3 cross 2 matrix is a syntax error. If a scalar is passed as an argument, then it will create a one-dimensional array. For example, passing np.1 5 will create a 1D array of 5 elements all initialized with 1s. Let's see some examples. So here we are going to create 2D, 3D and 4D arrays. So 2D with rank 2, 3D with rank 3 and 4D with rank 4. So A is equal to np dot ones of 4, 2, and let's specify its type as np dot int 32. So we just copy it and create another with 3 elements. So now a tuple with 3 elements means a 3-dimensional matrix. Input int, so float 32, and go and create another one, 2, and then we just go and print a dot shape, b dot shape, and c dot shape, and that's it. As you can see, now A has a shape of 4, 2, its number of x's is 2, B has a shape of 3, 4, 2, and C has a shape of 2, 3, 4, 2, 4D array. Third set of elements can be used to create arrays with random values. For this, we will use np.random modules. np.random modules are set of methods for sampling random values from different distribution. For example, np.random.ran generates samples from a uniform distribution. Similarly, np.random.randn can be used to generate samples from normal distribution with mu0 and sigma 1. So let's sample from a random normal distribution and plot histogram. So let's suppose, so samples is equal to np.random.rand, and so let's sample 25,000 samples, and then let's go and plot it. plt.list samples, and let's set number of win is equal to 100, and that's so simple it is. So Here we are sampling 25,000 points from random normal distribution and plotting its histogram. Third way of creating arrays to load data from files such as CSVs and TSV files. Once the data is loaded, we can cast it to np.arrays. For loading from the files, we'll be using functions load.txt. Load.txt expects that all the columns in the given file must be of either integer or float type. And we can also specify the delimiter we are going to use to separate the columns. So let's load some data, np.load.txt. And we're going to load data, and here we are going to mention that it's a CSV file. So print z.shape. Oops. Or backslash data.csv. Okay. So here it is. So now we have loaded. So we can even print the z as well. So here we have a two-dimensional array with 2 rows and 5 columns loaded from data.csv. Once we have created the arrays, our next logical step will be to understand and know what type of basic operations we can perform on these arrays. We can apply basic arithmetic, comparison, and logical operators on these arrays. For instance, in case of arithmetic operators, we can apply all the built-in Python operators on these arrays. In these operators, one of the operand can be either a scalar or an array where applicable. One important point to remember about these operations is that all these operations are applied element-wise. That means that we apply operation on each element of the array individually. For our first case, let's consider when one of our operand is scalar. Let's add, subtract, multiply, divide, and compute the power of each element of an array. So here is the given array. So we are going to add, multiply, print a plus 2. So a plus 2. Add, multiply. Subtract. Let's compute the power of. So here it is. So you can see that applying these operations result in new arrays with operation performed on each element of the array individually. In the second case, both the operands can be of array type. However, remember here you can only apply the arithmetic operators only and only if both the arrays either have same shape or their shapes can be broadcasted. We will see at the end of tutorial what broadcasting means. Let's see some example. Given these two arrays of the same shapes, I am going to apply binary arithmetic operators plus division and multiplication. So let's go and see. Print a plus b, comma a plus b. This will give us a new array where each element of the new array will be the result of sum of corresponding elements of a and b. Now go and do print a divided by b, which will be equal to a divided by b, and then print a multiplied by b. So here the resultant array will contain the element wise multiplication between elements of a and b. So let's run it. So here is the result of applying this operation. As in the case of arithmetic operators, comparison operators can also be applied on the arrays. These operations will be also applied element wise. However, these operations will return an array of type Boolean of the same shape as the input operand. So let's see some examples. So here, given two arrays a and b, I am going to apply comparison operator. So here I am going to apply the equality operator first. So let's go ahead and print a equal to b is equal to a equal to b. This will give us a new resultant array with values either true and false. If both the elements of array a and b has
same values, we will get true, and if the corresponding elements of A and B are not equal, we will get false. So print A greater than equal to B, comma A greater than B. So A less than B, A not equal to B. And finally, I am going to compare A with a single scalar value. This will result into comparing each element of array A with the scalar value. So let's do that as well. Print. Let's compare A with the value of 5. A shift not equal to 5. So let's run it. So here it is. So as already mentioned, this will return us a Boolean array of the same shape as the input array, where true will correspond where the comparison operator will be true, and false where the comparison operator will result into a false.
Naturally, after arithmetic and comparison operator, there come logical operators. However, NumPy uses its own functions like np.logicalNot, np.logicalAnd, and np.logicalOr for applying logical operators on NumPy arrays. It is important to mention here that non-zero values are considered true and 0 is considered false in Python. For example, let's go and apply logical operators on these two arrays. Print A and B is equal to, comma, np.logical and A, comma, B. So similarly, we can do A or B. A not B and not of A. So np.logical not of A. So here it is. That's as easy as it is. Now we have learned how to create arrays and how to apply the basic operations. Our next step will be how to index or access array elements. Array elements can be accessed via 4 different indexing methods. It is extremely important to master all these indexing methods to build realistic data science applications. Let's start with the basic indexing. The basic indexing is identical to Python indexing, where you can access any element by specifying the index value along each axis. For instance, if it's a single dimensional vector, we have to just tell the location starting from 0 to access the elements. NumPy, just like Python, supports both forward and backward indexing. Forward indexing starts from 0 and run to length -1, and reverse indexing starts from -1 and index number is decreased till the first element. Let's go and access the 3rd, 5th and 9th element of this one-dimensional array or one-dimensional vector. So we are going to access A of 0, A of 2, this is going to be the 3rd element, and A of -2. So here it is. So it's going to give us access to 3rd, 5th and 9th element of this one-dimensional array. In two-dimensional and dimensional case, we will have to provide indices values for all the axes. In comparison to Python list, we can give all the indices via comma separated list. For two-dimensional array, first index will be used to mention the row number and starting from 0, and the second index will be used to mention the column number starting from 0 as well. In the three-dimensional case, as the 3rd axis is prepended at the start of axis, so the first index will be used to mention the page number or matrix number, and second index will be used to mention the row number, while the 3rd index will be used to mention the column number. Let's consider the example of 2D matrix. So for accessing this second row first element, we will have to use A11 since the indices will be starting from 0, 0. So to access the first row last element, we will have to provide index A03. And similarly, to access this third row second last element, we will be using the indices 2, 2. Let's see some more examples. So let's go and extract the first elements of this two-dimensional matrix and then extract the second row and third element. So here I'm just going to print a of 0 0, and then I'm just going to print second row and what I'm asking, third element, so print a comma. So let's go and then print. So here, as I already mentioned, for 3-dimensional array, the first dimension will be used to index into matrices. So here I want to access the 0th matrix, first row and 0th column. So I am just going to write a of 0, comma 1, comma 0. So here it is. So here is the output of these operations. Next comes slicing. Slicing allows to manipulate more than one elements of an array. It is one of the most important tricks to master while working with NumPy. One thing which we always need to remember when working with slicing is that it returns view of the underlying data. So if we do any updates on the extracted slice, it will be reflected in the original array as well. However, before understanding the slicing, we will have to understand the Python sequence generation syntax for slicing. For generating a sequence for a slice, Python expects 3 elements separated by colon. It is starting index, it's the ending index which is excluded from the slice, and the step size. By default, step size of 1 is used. For example, 1 colon 3 colon 1 will generate indices 1 comma 2, since endpoint is always excluded. Let's see some more examples. So let's print a 2 to 4 will select third and the fourth element from this 1D array. We can select as well as update a slice value. So let's go and update slice value. So let's go 3 to 8 with step size of 3 and set its value of equal to -1. We can also accept the slice using reverse indexing. So let's suppose print a -1 colon -5 with the step size of -1 will give us the last 4 elements. And similarly, the view updation, it's an important concept. So if we copy a slice A, let's suppose up to 0 to 5, and then if we update its values, z of 1 to, so 0 to 3 is equal to -20, and if we print the original array, print A, this change will be also reflected in it. So here it is. So here is the output of all the slicing operation we have performed. If we exclude the starting point during slicing, by default 0 is considered as the starting point. Excluding the end point means all the element indexes till the last element which will be included. For instance, so let's go and do print A till colon 3 will print the first 3 elements. Similarly, if we go and use print A 4 colon, will start printing from the 5th element till the last element of the array, for example, as can be seen. So it will be printing the last 5 elements. Similarly, colon for an axis means all the elements of an axis, and colon for all the axis means, so here is a differentiation between and all. Colon for an axis means all the elements of an axis, and colon for all the axis means collapsing the array in a single dimension. It's very important point to remember. For example, in 1D case, writing print a colon will print all the elements of the array since there is a single axis. Same generation or same index generation syntax can be used for 2D and n-dimensional arrays. However, now we will have to provide sequence generation syntax for each axis. For example, for a 2-dimensional array named as A, using 0, 1, column 3 will now return first row, second and third column elements. Here we are using slicing on axis 1. Similarly, using slicing on axis 1 but with a different row number will return second row, first and third column elements. Here we are once again using the slicing index, but now we are using both slicing across rows and slicing across columns. A 2 column will return all the rows starting from the third row, and 1 column will return all columns starting from the second column as highlighted over here. There is a mistake over here. Please note that it's 1 column, not 2 column. A colon comma colon will return the complete matrix, as I have already mentioned that using colon for n axis will return all the elements along that axis. Here we are using a colon comma 0 colon 3 colon 2. So here we are using complete slicing against rows and selecting particular columns. So this syntax will return the complete first and second columns. So first and second column means 2, 6, 10, 3, 7, 10. Here we are using now, here we are slicing across rows and then we are selecting all columns. So a column 2 will return the 0th and the first or the third row with complete set of columns. So the answer of this syntax will be 1, 2, 3, 4, 9, 10, 11 and 12. A column will collapse all the dimension to a single dimensional vector. So let's go and see some example. So for example, given this 3-dimensional array, we can get the complete collapsed array by just using a column. So if we have to select 0th matrix, second column, so first we are going to put 0. So we are basically selecting 0th matrix, and then we have to select second column. It means that we have to select all possible rows. So I am going to put colon in along that axis, and then it's the second column, so I'm going to put 1 over there. So similarly, select first matrix, second row. So here our syntax will be a1 comma. Now I have to select first matrix, so I am going to put 0 and I'm going to put second row, so I'm going to put 1 over here and I'm going to put colon across the third axis or the second axis if we start the indexing from 0. So if I go and print these elements, so here you will see all the result of these indexing operations. This completes our discussion of slicing. Next important type of indexing is Boolean indexing. In Boolean indexing, we use a Boolean array as indexer. Numpy will return a 1D array with values copied from the array wherever there was a truth Boolean value in the indexer. So Boolean indexing can be applied over any specific axis as well as over the complete array. Remember, the Boolean array must match the shape of array or the axis on which it is being applied. Let's suppose that we want to select these elements from this 2-dimensional array. So what we are going to do is we are going to create a mask with values set to true corresponding to the elements which we want to select and false against all the elements. Now once we have this mask, which is the same shape as the input array shape, we are just simply going to pass this mask to the array, and Boolean indexing will select those elements and return us a single 1-dimensional list. Remember that this Boolean indexing doesn't work with the multi-dimensional indexing. For this, we have to use an advanced version of this function, which is basically np.ix. However, we can apply it on specific axis or along specific axis, selecting particular rows and columns based on specific values. Boolean indexing is one of the most important tools to master to make your code fast and vectorized. So let's see some examples of Boolean indexing. So let's suppose here we are giving an array and I would like to set all the entries less than 0 equal to 0. It's an absolute function. So I am simply going to create a mask. So first I'm just going to print a is equal to a, and then now I'm just going to create a mask and I'm going to use that mask as index. So now the expression a less than equal to 0 will give us a Boolean array which we are going to use as indexer into the original array a, and I'm just going to put all these values equal to 0, and that's it. That's how the Boolean indexing works. So a is equal to, so let's see the result of. As you can see that using this very simple method we can filter out all the values whose magnitude was less than 0. Let's see another example of Boolean indexing. In this example I'm going to consider A as a training matrix, in which there are 5 training examples and each example has 5 features. So I'm going to use Boolean indexing to select example corresponding to a particular class. For this case, I'm going to assume that we have been given a label array. In this label array, example corresponding to the positive class has label P and example corresponding to negative class has label N. Now I'm going to use this label array to select positive example from the original training matrix A and negative example from the same matrix. So how I'm going to do that? Simply, I'm just going to create a Boolean mask for negative example and we'll take the complement of it for selecting the positive example. So let's go and create the mask. So negative labels will be equal to labels is equal to N. And then it's very easy to select positive examples or negative examples. Negative examples will be equal to A. And now I have to choose specific examples. So as examples are stored row wise, so I am going to apply this Boolean indexing along axis 0, which means along the rows. So negative labels, and then I'm going to select all the columns. And to select the positive examples, I'm just going to take a complement of negative labels. So here I just go and create positive labels is equal to np dot logical not of negative labels, or you can also use labels is equal to P. So here I am going to use positive labels. That's how I'm going to select positive and negative examples. As you can see, where there was N, there was 2 negative examples, so there are 2 rows, and there was 3 positive examples, so there are 3 selected rows. That is as easy it is. Finally, the 4th type of indexing is named as fancy indexing. In fancy indexing, we can provide a list of indices for the elements of our interest. For instance, for this 1D array, our elements of interest are, let's suppose, 1st, 4th and 8th element. So we'll create a list with the indices of our element of interest, and we'll pass that list as indexing list to our array, and NumPy will select the elements corresponding to our interest and will return us a 1D array. We can even select elements from multi-dimensional arrays by passing a list of indices for each axis, and it will return a 1-dimensional array of selected elements. Let's suppose that we want to select this, and this element from this 2-dimensional array. So here we will create 2 lists, one for row axis and one for column axis. We will fill these lists with values or with indices of values of our interests. For examples, our rows of interest are 0, 0 and in fact rows of interest are 0, 1, 2, and our column of interest are 0, 0 and 2. We'll pass these 2 lists to NumPy array as fancy indexing lists, and NumPy will make pairs from the corresponding elements of these lists and use these pairs for indexing into the original list or original ND array to return us a 1D array. Now let's see some example of fancy indexing. So given this 1D array, let's select 4th, 3rd and 2nd element. So I'm just going to pass print A, and I'm going to pass a list with 4, in fact 3, 2 and 1 to select the 4th, 3rd and the 2nd element. So similarly, to select A 0, 0, 1, 0 and 2, 2, I'm just going to create 2 lists and will pass those 2 lists as fancy indexing list to this 2-dimensional array A. So let's do that. Print A of A selected is equal to, I'm just going to use A of 0, 1, 2, and I'm just going to use 0, 0 and 2. So that will just select 0, 0, 1, 0 and 2, 2 elements from our array. So here is the output of it. So it will return us 0, 3, 8, and in the first case it will return us 3, 2, 1. So here is 3, 2, 1 elements from our this array A. Now once we have covered The indexing in detail, we would like to dive a little deeper and see how the arrays are stored in the memory. Specifically, all the arrays are stored as linear arrays at the back end. They are stored either in row measure order or in column measure order. Row measure order is also referred as C order, and column measure order is also referred as the Fortran order. In a row measure order, first row of a multidimensional array will be stored first, followed by the second row, and so on. In contrast, in a column measure order, first column of a multidimensional array will be stored first, followed by the second column, and so on. Understanding this organization is extremely important, since this can help us to correctly visualize array shape manipulation. Specifically, when working with data coming from different sources, this understanding of array storage organization can really help us to debug our code. Array shape manipulation is one of the most frequent operations that we will perform while vectorizing our code. Array shape can be easily manipulated via either an in-place operation or by using the reshape function. We are going to see both examples. But one thing we have to remember is that the array shape manipulation will always create the view of the existing data. It's not going to create a new array. Secondly, we have to remember this, that while reshaping, the number of elements of the new array have to be the same as of the existing array. That is, the number of elements can't change. Conceptually speaking, given this array of shape 4, 3, it can be transformed to 3 new arrays of either a shape 2, 6, 6, 2, or a shape 3, 4. While reshaping from 4, 3 to 2, 6, it will be done in a row measure order. That is, the first row of the new array will be filled by picking the elements from the previous array in a row-wise manner. Then the next row of this new array will be filled by once again picking the remaining elements from the previous array in the row-wise order. Similarly, this array can be reshaped to this new shape of 6, 2 by following the same procedure. That is, first we will be filling the first row of this new array by picking the elements from the existing array in a row-wise manner, and then we will fill the second row and third row, and so on. NumPy gives us 2 ways to reshape the array. The simplest way is to simply update the shape data member value to new shape. So for example, given this one-dimensional array, we can very easily reshape it to a 2-dimensional array. We are simply going to reset its shape data member to the new value 2, 2. Can also print like that. So that's it. The second way is to either use the member function reshape or NumPy global function reshape. Let's reset the shape of y to 1, 4 using the member function reshape. Member function reshape expects the new shape as argument. So let's go and reshape y dot reshape. We are simply going to reset it to its original value 4, 1 using the reshape member function. Let's go and create a new array z.np.a of 24 and reshape it using the global reshape function. The global reshape function expects from us 2 arguments: the array to be reshaped and its new shape. So let's go and reshape np.reshape z, and let's set its new shape to 2, 6, 2, and assign it to a new variable w. So print y.shape and w.shape. Here it is. Next comes tiling and stacking. Tiling and stacking helps in code vectorization. There is a very small difference between tiling and stacking. In tiling, we append the existing array row-wise or column-wise or across any specific axis, while in stacking, we append different arrays into a specific array along rows, columns, or a specific axis. As already mentioned, tiling and stacking concerns with the axis. So stacking across axis 0 means we are appending new arrays to an existing array row-wise, and tiling along, or in fact stacking along axis 1 means we are appending new arrays column-wise, and stacking across axis 0 means we are appending new arrays depth-wise.
np.tile is used to create new array via tiling. np.tile expects an array as and a tiling tuple as arguments. So let's create a new array by tiling this existing array vertically. So b is equal to np.tile. So a. So we are going to provide tiling tuple as second argument. So since we are tiling across or tiling along axis 0, so we are going to provide 3, 1. So this tuple will force or will create a new array b by copying this existing array 3 times along axis 0 and 1 times along axis 1. So here let's print it, print a b dot shape. So given this a new array z, let's tile it in the depth dimension. So tiling in the depth dimension, I can use new z is equal to np dot tile. So z comma 3 comma 1 comma 1. So using this as tiling tuple, we are asking the numpy to copy this existing array z 3 times in the depth dimension and 1 times along axis 1 and 1 time along axis 2. So let's go and print nz and nz dot shape. So here we are. So as you can see, so 5 5 5 5 5 5. So we have created a new array by copying this z array in depth dimension or along axis 0. Stacking helps to create new arrays. For stacking, 3 different functions are used. np.stack is used to stack the arrays vertically, where all the arrays must have the same number of columns. np.hstack is used to stack the arrays horizontally, where all the arrays must have the same number of rows. np.concatenate is the generic version and can be used to stack arrays across any axis. Let's see some examples of vertical stacking. So for vertical stacking, we are going to use np.vstack. So let's suppose c is equal to np.vstack. All these function expects the stacking arrays as a single tuple argument. So we are going to provide a comma b. So this is going to stack b below a. So print a comma b comma c. So here you can see, here is the a, here is the b with 6 3 4 5 6 7 8, and then you can see 0 1 2 3 4 5 6 7 8. These are the values of our stacked array from a and b. So let's see some example of horizontal stacking. In this case, the number of rows must be same. So for that, we are going to use np.hstack. So c is equal to np.hstack. A comma b. As in vstack, we are also providing a tuple argument with all the arrays to be stacked horizontally, provided via comma separated list. So print a comma backslash n comma b comma backslash n. So here we are. So as you can see 0 1 2 3 4 5 6. So here we have 2 arrays with the same number of rows, and by stacking it horizontally, we can create a new arrays with content from both the arrays. The next topic we are going to cover is about universal functions. Universal functions are ufunc, or the functions which are applied element wise on the array and return an array of the same shape as the input array. These universal functions return a copy of existing array instead of view. Numpy has more than 60 universal functions. There are 2 types of universal function, unary and binary universal functions. Unary universal function expects single array as an argument and return an array of the same shape as an input. The output type of array can be either of same type or Boolean. For example, functions like sine and exponent will apply the requested mathematical operation on each element and will return array of float type. In comparison, function like isnan will return a Boolean array filled with true values where there is a nan and false otherwise. Let's see example of universal functions. Here, given this array z of shape 2 comma 2, I am going to apply a list of universal function on it, and we are going to see the results. So for fn, so let's create a list of these universal functions and simply f of z is equal to, so I'm just going to create the placeholder for string formatting, and then I'm just going to fill it with the values. So f dot underscore name comma f of z. So here is the output of applying the requested operation on this input array. So applying sign of z on this 2 array with values in the range 0 to 3 return us these values. So as you can see, is nan will return false corresponding to all the values corresponding to all the location where there is no nan, and if there is nan, it will be returning true. Binary universal function work in the same manner as unary universal function. However, they expect 2 arguments instead of 1. 2 functions here are of quite importance: np.maximum and np.minimum. They both compares the value of both the input arrays element wise and return the maximum element among the compared element. These np.maximum and minimum can be also used with scalar values. Binary universal functions work in the same manner as unary universal functions. However, they expect 2 arguments instead of 1. 2 functions here are of quite importance: np.maximum and np.minimum. np.maximum compares the elements of both the input arrays element wise and return the maximum element. np.maximum and np.minimum can have scalar as their input argument as well. Let's see an example of np.maximum. We are going to use it here to clip the values of array by comparing all the values of the array element wise with 0. So let's go and do that. Z is equal to np.maximum y comma 0. So Z will now contain maximum between each element of y and 0, and since the first 4 values of the y are greater than 0, so we will be getting 1, 3, 4, 7, and the last 2 values of y are less than 0, so we will be getting 0 corresponding to those 2 values. So let's see, print z. So here it is. Numpy also provides set of summarization functions. These functions can be either applied on the complete array, which is their default behavior, or can be applied on specific axes. For example, let's study the sum function in detail. Applying the sum function over the complete array will return the sum of all elements, which here is 45. Applying the sum function over the axis is equal to 0 will sum the elements along the rows and will return 1 cross 3 vector containing sum of each of the column. Applying the sum function over axis 1 will return a 3 cross 1 vector containing sum of each row. All these functions except keep dim as an extra argument. By default, its value is false, and that's why it is recommended that initially you set it to true to force these functions to produce the same dimension as expected. Otherwise, the dimension along which the operation is being performed will be collapsed, and your resultant array will have your resultant array will have 1 less axis. Let's see sum function in practice. So given this 2-dimensional array, let's first get the sum of all elements. Print sum of z. So we can go and print z and print sum of z, and then let's go print the sum of all the columns. Sum z is equal to x is equal to 0, and print np dot sum of z is equal to x is equal to 1. X is equal to 0 means we are summing along the rows, and x is equal to 1 means we are summing along the columns. So here it is. So as you can see, so we got the same answer, 12, 15, 18, 21, which is the result of summing all these values. And when summing across the columns, we will get 3 cross 1 vector. So we can also force them to have the same dimensions, that is keep dims is equal to true. So here it is. So now you can see that now we have the same type of dimensions as we were expecting. Now what if we want to find the indices of maximum or minimum elements in an array? Numpy provides function prepended with words arg. For example,
argmax or argmin will return not the maximum or minimum elements of array, but will return the indices of maximum and minimum elements. Let's see argmax in action. So for example, given this 1D array, we want to find the index of maximum element. So we are just going to use np.argmax, and it's going to return us the max idx. Using this, we can then find the maximum elements. So print a comma max idx, a of max idx. So here it is. So as you can see, the max idx is 7, so it is 0.9965, and here is its value. So let's use once again argmax to find maximum elements in each row with their indices. So let's suppose we are given this two-dimensional array. Now we are going to use argmax, but now we are going to use it with axis argument. Using with axis give us the indices of maximum or minimum element along that axis. So let's go and find the indices of maximum element in each row. So max idx is equal to np.argmax a x is equal to 1. This will return maximum element index in each row. So let's go and print a max idx, and then I am going to use fancy indexing to display the maximum element in each row. So a of np dot. So since I am going to select all the rows, so I am going to np dot a range of 5, and then I'm going to go with max idx. This index here, corresponding to each row, I am providing one maximum column index. So here it is. So as you can see, the maximum element index in first row it is 1. Basically this is 0.89000375. In second row it's 2, which is 0.94. In third and fourth row they are the 0th element, and in the last row it's the last element, which is 0.90. And then this syntax is responsible for extracting the maximum elements from each row. The first, as already explained, the first sequence is being used to generate all the row numbers, and they are paired with each column index to find the maximum element in each row. Remember, NumPy provides two functions for computing maximum and minimums, max and maximum. Max accepts a single array as input argument and returns the maximum element of the array along any axis. In comparison, np.maximum receives two arrays, or an array and a scalar, and performs maximum operation element-wise on the given input arguments. Other operations such as sorting the arrays, finding a set of unique elements, or set operations can be done using the similar syntax. Let's see an example of sorting. Let's first sort an array and then find the sorting indices and use those indices to sort the array. So for sorting, I am just going to use np.sort, sort of a. So sorted a is equal to this. Similarly, I can use an argsort version for finding the indices of sorted elements. So sorted indices will be equal to sorted indices is equal to np.argsort of a. Here I can also provide axis and extra argument, as we have seen in the case of some function. So let's see, print a sorted a. This will be SA will be the sorted array, and print sorted indices, and we can also print a sorted using the sorted indices. So here is the output. So here is my original array, and then here are its sorted value. NumPy also provides built-in functionality for performing basic linear algebra operations on the array. Extended operations such as finding the inverse of the matrix or applying singular value decomposition can be done by using the function from the linear algebra package of NumPy. For more advanced operations, one can import CPy linear algebra packages and use them to perform more advanced operations directly on the array. Let's start with matrix transpose. Each array has built-in attribute .t. that returns the transpose of the matrix. For advanced operation, one will need to use the np.transpose function. Remember that .t attribute returns the view of the array data, not a copy. So let's see .t in practice. So let's create a new matrix A, which is the z.transpose, and let's go and print A dot shape and z dot shape, and then I'm going to update the 0th element of A with a negative value, and then I'm just going to print z to show that .t is actually a view, not a copy of an array. So since in our original array all the elements were with positive value, you can see that changing A has modified the original z array. For calculating matrix vector or vector products, Numpy provides a function named as dot. For applying this function on the arrays, the inner dimension of the array must match, otherwise it will raise or generate a syntax error. Let's see the dot in practice. We are going to use dot to compute dot product between two vectors. If both the input arguments to the dot are vectors, only the number of elements in the vector has to match. So let's suppose b is equal to np dot dot a comma a print b. So for computing the matrix vector or matrix product, the inner dimension must match. So here we are given a two-dimensional matrix and we are given a column vector, so we can take a matrix vector product. So let's suppose matvec is equal to np dot dot c comma d. So here and we can print matvec product is equal to matvec dot shape, and here you can see the output of this this dot product, and it will be 2 cross 1 vector, as can be seen here, where it has 2 rows and a single column. For calculating vector norms and applying advanced linear algebra operations, we will be importing the linear algebra package. Let's first use norm function from the linalg package to compute L2 norm of an array. So for example, print x comma linalg dot norm of x. So it will return the L2 norm of the x. So as you can see, so here is the original vector or original array x, and here is the L2 norm. In addition to the norm function, there are many other built-in functions in linear algebra package. Let's use the svd function to decompose the matrix into its 3 constituent matrices u, s, and v. Here u and s. So first let's do it. So u comma s comma, so v is equal to lin dot svd of a. So we are applying this svd singular value decomposition on this 2 cross 2 matrix, which will be returning 3 constituent matrices u, s, and v. Here u and v are full matrices and contains the orthonormal basis vector for the column space and row space of the input matrix A respectively. S is a unit axis array and contains the singular value. Let's see it. So S basically contains the singular values in the descending order, sorted in the descending order. U and V are also arranged according to the contribution matrix S. Numpy also provides built-in support for saving and loading the data into and from the files in both text and binary format. For saving and loading the data from binary format, it provides the pair function np.save and load. Both these functions save the data in the numpy npy format. One can save multiple arrays by passing them in the form of a list or a tuple to the save function. Let's see the save and load in action. So here I am given 2 arrays, so I am going to save them to the file np.save. The first argument is the name of the file to be saved, so I am going to put it in data.npy, and the second argument is a list of arrays or tuple of arrays we want to write into the file, so z comma y. So it's that easy it is. So that's it. So it has saved z and y into the file. For loading, we will simply using np.load, and it will return us
list, and here we are just opening this list into two separate arrays, z and y. We name it different, a comma b. So a b. So here, oops. Oh. So print a, print b. So here it is. So that's how easy it is to write to the file and load from the file. For saving and loading the data in text format, one can use save text and load text functions. Save text and load text also take delimiter as another argument. So let's see, for example, to save the array z into the file, we are going to use np.savetext. The first argument is the name of the file. The second argument is the array which we want to write to the file, and the third argument is the delimiter we are going to use to separate different elements of the array. So let's write it. And then for loading from the file, we will be using the corresponding function load.txt. The first argument is once again the name of file where we are reading from, and the second argument is the delimiter which we specified at the time of file writing. By default, if we don't provide any delimiter, it's considered to be the space. So here we can just load it. Oops. Z. So here it is. This completes almost our tutorial on introduction to NumPy, except one of the most important topic and an extremely easy topic of broadcasting. NumPy has this built-in inherent functionality that when applying the operation on the arrays, if the shapes of the arrays under operation mismatch, it applies broadcasting rules to match the rank and shapes between the arrays. For example, let's say that we want to add this one-dimensional array A to this two-dimensional array B. So technically speaking, adding A plus B should raise a shape mismatch error. However, NumPy solves this shape mismatch problem automatically in majority of the cases by following the broadcasting rules. So let's run this code, and as you can see, NumPy has been able to automatically infer or resolve the shape mismatch error by following the broadcasting rule. So let's go and see what are these broadcasting rules.